career, I've seen tons of Southerns, Northerns, and Westerns. I've done tons of Northerns and Westerns. I've done a couple Southerns. I have seen in the literature 2 far Westerns. I have never seen a Northwestern or a Southwestern, but they are done. But like I said, all I guys want you to remember is DNA is Southern, RNA is Northern, and protein is Western. So the first step in performing a Southern blot is to digest the DNA with restriction enzymes, usually. And so this serves 2 purposes. The first purpose for digesting your DNA sample is that basically whenever you're doing a Southern, you're restriction mapping something, just like you guys already did with the plasmid DNA. And so digesting our sample with restriction enzymes allows us to look for a particular banding pattern. So just like you guys picked the enzymes that you used for restriction mapping PGLO, based on the PGLO sequence, you're not randomly digesting your sample. You are, especially with human genomic DNA where we now have the sequence, you are picking enzymes that should give you a particular banding pattern, depending on what you're looking at. We'll talk about a little bit more about that in a second. The more general reason you digest the DNA in a Southern is just to make sure that the genomic DNA will run into the gel. Remember, genomic DNA is huge. These chromosomes are massive. And so we didn't get to this point in the gel electrophoresis lecture. We'll talk about it next week, or Thursday if there's time. But you have to use a special type of electrophoresis to separate chromosomes on an agarose gel, pulsed field gel electrophoresis. For Southerns, we don't do that. For Southerns, we run normal agarose gels. And so in order for the DNA to even get into the gel, we have to cut it up. We have to make the pieces smaller. So I'm going to turn the lights back on. Because one of the things I want to talk about is how do you choose the enzymes you use to digest your DNA? So the lab that we're continuing from the Thursday before spring break is we're looking at the presence or absence of this PV92 allo element on chromosome 16 by PCR. Well, you could do the same thing by Southern blot. So let's say we've got two possibilities, right? We can either have chromosome 16 with the PV92 element or chromosome 16 without the PV92 element. So, oh, I didn't talk about what this table is on the slide, excuse me. This table is from the New England Biolabs website, the people we get most of our restriction enzymes from. And basically all it is given different species from E. coli all the way up to humans. It gives the frequency in those genomes with which each of these enzymes cuts. So, NOT1 cuts approximately every 130,000 base pairs in the human genome. It doesn't cut very frequently. In contrast, I can't even read this. FSE1, oh, no, not FSE1. HinD3 cuts every 4,000 base pairs in the human genome, on average. Remember, these are site-specific endonucleases, so they do cut a particular sequence, but on average, they cut every HinD3 cuts every 4,000 base pairs. So let's say we want to do a Southern blot to tell if someone is homozygous positive, homozygous negative, or heterozygous for the PV92 allo element. So if you wanted to do that, I know we haven't talked about the rest of the blotting procedure, but we're going to restriction map this section of chromosome 16. So where would you choose enzymes? Where would you want your enzymes to cut this piece of DNA to tell if someone, just like your PCR, to tell if someone is homozygous positive, homozygous negative, or heterozygous for the PV92 allo element? Any ideas?
cut the P92.
So you want to cut where? Just here?
No, from beginning and from the end of P92.
The whole section.
Okay, so you have, so we want to cut with something kind of here, or Lee wants to cut with something here and here. Okay? So then what's the banding pattern going to look like if they're homozygous positive for the PV92 element? And you have to remember that nothing is going to be completely unique to the PV92 element. These enzymes, whatever Lee is suggesting, are also going to cut somewhere outside as well. Okay, Lee, so what's the banding pattern, or not just Lee? If we use Lee's enzymes here to cut close to the beginning and end of the PV92 allo element, what's the banding pattern we're going to see when we look at this? How many bands are we going to see?
3.
Well, okay, so let's say we're looking at this region, it cuts in those places that I marked. So let's say we're going to probe for just this piece of DNA. And we'll get to how we do that in a second. So in that case, we're going to have 1, 2, 3 pieces of DNA, right? So we'll get something, so homozygous positive. It's going to give 1, 2, 3. And while I haven't, the way I've drawn this, these are all exactly the same size, let's assume they're not. Okay, so what's this going to look like if the person is homozygous negative? You get 2?
No, still have.
Hmm?
Just one. Still has 3.
So we're missing this chunk in this piece of DNA. So this restriction site is going to be here, and that restriction site is now going to be here because that 300 base pairs is missing. So now, basically going to see one piece of DNA, right? And depending on where they cut, we're not exactly sure how the size is going to be different. And so that if they're heterozygous, which means they have both this chromosome and this chromosome, what are we going to see? Yeah, we're going to see all those bands. So if they're all different sizes, that's great. So Lee's method will certainly work. So at the end of class today, or possibly on Thursday, depending on how far we get, I'm going to show some examples of actual Southern blots from papers, and we'll talk about how to interpret the results. But one of the things you can look at with a Southern blot is, like I said earlier, you can look for a different banding pattern. So for the PV92 allo element, if we use enzymes that kind of cut the whole allo element out, one of these bands is going to be about 300 base pairs, because that's how big the allo element is. The other 2 bands, it's going to depend on how close these enzymes cut outside the PV92 element to that element. And so these could be 150 base pairs, they could be 3,000 base pairs. So it depends on what enzymes you use, depends on where it is in the genome. So in this case, it should be really obvious that homozygous positive gives one banding pattern, homozygous negative gives another banding pattern, and heterozygous gives a third banding pattern. So you would be able to tell, aside from PCR, you could tell by Southern blot, based on the enzymes you use, someone's genotype for the PV92 allo element. So let's think about something else. Another example. So there are other options for the PV92 allo element though. So let's say, actually, let me do this again. How else might you, how do I say this? Well, I'll come back to it. We'll talk more about programming and how to analyze Southern results. Let's say we want to look at a SNP or a point mutation. So here we've got a TA base pair and it's a SNP. So here we've got a CG base pair. So if you want to look at this SNP by Southern blot, what would you have to do?
By using the probe. Just call it.
Well, yeah, I mean, but all Southern blots use a probe. But you have to be able to. But right now we're talking about choosing restriction enzymes. So where would the restriction enzyme you choose have to cut this to be able to tell the difference between these guys?
Exactly at the DA.
Right. So the restriction enzyme has to cut, the restriction enzyme sequence has to include the SNP. And so, depending on the restriction enzyme, it would cut one or the other of these, but not both. And so, if the restriction enzyme cuts this, so we get a cut there, and then you get some kind of cuts outside this region. And depending on how big a piece of DNA you want to look at, if you want to look at 500 base pairs, do you want to look at 2,000 base pairs, do you want to look at 10,000 base pairs? If the restriction enzyme cuts this allele, you're going to get 2 bands. And then this guy is just going to give you 1 band. That's going to be bigger than, it's going to be the same size as the sum of those 2. So again, this would be fairly easy to tell if someone's homozygous or heterozygous. Because this would be homozygous for the TA, this would be homozygous for the CG, and if you see all 3 bands, then they'd be heterozygous for the SNP. So one of the most important things that you can do when designing a Southern blot is pick the restriction enzymes you're going to use so that the results of your Southern blot are meaningful. That depending on what you're looking at, you can see a difference in banding pattern or band intensity. We'll talk about that a little bit later. With the restriction enzymes that you're using. And so, it used to be that it was much harder. Before 2000, 1998. Or how should I say it? The Human Genome Project made choosing your restriction enzymes much, much easier. Now that we have the genome sequenced, you can intelligently, specifically choose restriction enzymes you want to use. Previously, people would digest sequences with a bunch of different restriction enzymes and see which pattern gave them the most useful information. You guys won't have to do that. So, in a Southern blot, what happens after we digest the DNA? What's the next step? Exactly. So, write all these down on the board. This is what I'm used to. Right. So we take our genomic DNA, digest it with restriction enzymes that are going to give us a recognizable pattern that we expect based on the sequence we want to look at. And then we do electrophoresis. For most Southerns, almost all Southerns, you're going to run an agarose gel. These are big chunks of DNA that we're looking at. We're going to run them on an agarose gel. I'm going to turn the lights out.